Hello. All right, so now what I want to do is I want to give you some guidance on homework one. Uh, I usually do this in lecture, so here we are. Um, this helps give some more explanation and some guidance. All right, I'm just repeating myself. Clearly, I think I'm losing it. Um, so what you're going to receive is a Gzipped file. And Gzip is predominantly found on Unix platforms as a good compression utility. So you give Gzip a file, it runs and it finds out a way to compress it, and it stores it in a compressed state such that Gzip itself then can uncompress it for you. Now, one of the important things about this is homework one tells you not to do this, is not to unzip the whole thing. There's no reason to do that. We can keep it stored compressed on your file system, so not taking up that much space. Also, we can read it faster because we have less material to read off the hard drive. And even though we have to use the CPU's power to uncompress it, to read it, we can actually do that faster because often hard disk drives are quite slow. Now, of course, you might have a personal computer with a solid state drive. I don't know if the trade-off is quite the same there, but in general, we keep things compressed on the hard drive because getting it off of the hard drive then is sped up, even if we have to use CPU power to make this possible. And then so what you're going to need to do is find for the programming language you have, which is you want to use a library. It'll be built in, or it should be. Usually it is because it's such a common format. But you can use the library to stream the file in and uncompress it on the fly. Don't uncompress it on the hard drive. All right. Likewise, if you don't listen to me on this first step and you're like, I'm going to uncompress the doggone thing. You're like, I want to see this thing. So then the next thing students do when they don't listen to me is they try to open it up in a text editor. So don't try to open it up in a text editor. Why? What happens? Well, what happens is text editors aren't that smart. And before they show you anything on the screen, they read the entire file into RAM. This thing is hundreds of megabytes large. It just doesn't fly. Maybe your computers are nowadays powerful enough, but in past years, students report things just hang. It causes horrible problems. They're not text editors are not designed to edit such large files. So don't do that. We do provide you a small sample so that you can practice with it or just view it. I'd say view and debug with, all right? Because it's helpful when debugging to actually see what you're working with. All right. Now, I've already said this verbally, but I didn't write it. I guess that was the point. But I did. I said to stream it in and uncompress it. But what I didn't say is do not read the whole thing into RAM. You don't need to do that. I mean, and think about if you were working with a web collection. So you basically have had your crawler collect all these documents on the web. You can't fit the web into the memory of a computer system. So that doesn't mirror the type of processing that other people need to do. All right, and so the idea that we're going to have here is to process the file. So the file is composed of a bunch of documents. Process it one document at a time. And we're going to do this by reading one line at a time. And only storing in RAM one document's worth of text at a time. So the idea is, we're going to open this file up, stream it off the disk, uncompress it on the fly, read it line by line, and once we've read enough lines that we're like, ooh, that's one document, we're going to go on and process that document. Then we're going to get rid of that from RAM and keep reading again until we've read another document, process it, and repeat this process until we're done with the file. This is quite an efficient way. The nice thing about it also is it's very linear. You just stream through, read the whole file from end to end, and then you're done. We love things that are time complexity linear. That's about as fast as you can go because you have to process all the data. So great, it's linear. It's wonderful. Let's keep it that way. And also this setup allows the RAM usage to stay extremely low, or as low as we can keep it. That also, things run faster when we're not putting too many more demands on RAM. Certainly not so that they're having to page in and out. All right, so let's talk about the format of this file. So this is what we call, it's in text format. Now, it's almost legal XML. Now, once upon a time, you might say, oh, XML, that's nice. Now people go, why, oh, XML? And it's, in fact, it was based upon SGML. This was a markup language prior to HTML, the hypertext markup language. So if you've ever bothered to look at the source code for web pages, hypertext markup language, HTML, you're going to see a lot of similarities. And XML clearly is, HTML is a subset of XML. Now, why do I say it's almost legal XML? The only thing missing from this file is a set of enclosing tags at the beginning and end. So it is a whole series of tags, and all those tags are all nicely legal and properly done. But the whole entire document, to be a proper XML document, needs one tag at the beginning and a closing matching tag all the way at the end, and this file does not have that. And so it is not a proper full XML document. You don't need XML tools to read it. So I'll say that. So you don't need XML tools to read it. Processing it line by line with doing some simple string comparisons or other string operations to extract stuff is really easy enough. But if you want to, once you've read one document in and you have it represented as a string, it's easy enough for that to be a legal XML document, and you can very nicely go and put that into an XML library processor, and you can then fetch things out of it based upon the tags using the XML processing without you having to parse the XML yourself. Now, it's not hard to deal with these file formats, but that is one sort of methodology, which is you could read one document's worth, put it as one string, and then hand that string to an input function to an XML reader. And the XML reader will go, oh, yeah, I understand all of that. And then you can query that XML reader for the properties of the document and get them out quite nicely and you know that you've properly parsed the document and not made any mistakes, because most of the processing will be done by the XML thing. And I actually believe that that's a wonderful thing to do. You really shouldn't ever spend your life learning how to parse XML. Leave that to other people. As far as I'm concerned, it's really if you're into compilers and languages, great. Learn how to do that sort of parsing. But otherwise, it's best to leave that stuff to existing libraries. So that's an example. Clearly, we had some questions. I've had some questions. Oh, what can we use and not use software-wise? That's an example. Absolutely. Use that. So I will say, but an XML reader is great for parsing an individual document. And I've certainly written that when I've done my own code. I've done it that way at times. Okay. So these files, this one file, but you get one file, contains a series of documents, one after the other. And each document is denoted with doc tags. So you're going to see a document start with a tag that's doc, D-O-C, and then you're going to see the document. There's going to be stuff in between it, and then you're going to see the document end with an end tag that matches. And the end tags, like HTML, are always /tag name, whereas the start tags are just the tag name inside of the less than and greater than signs. All right. Now, what else is inside of these documents? Well, they have inside of them, we need, when we're working with this system, and we're going to do information retrieval experimentation, we need to keep track of which document is which. And this is separate, keeping track of which document is which is separate from the internal representation that we want. Again, we want an integer for the internal representation. But for the external representation, each document is given a string identifier, and we call that the docno, or document. It's like document number, although it's NO, so I'm not quite sure why it's NO. But anyway, the docno, and that's our identifier. And when we record other properties that we'll give you about these documents when it comes time for evaluation purposes, it's per the docno. All right, so we have to retain and be sure to extract that information. So we talk about it as the ID of the document, or the identifier. The ID of a doc is given inside of the docno tag, as I was saying. Now I want to note something very critical. This is not the doc ID tag. Alert, super triple duper alert. Ignore this one. This is the one that you want, okay? It sure does look like we want this one. It says it's the doc ID tag. We don't. This is a document, the doc ID is a document identifier from the LA Times. That's not what we're looking for. We want the one that the National Institute of Standards and Technology gave it. We want the docno tag. All right. Then the tags with useful text material. So not all the tags are useful for us, but we want the ones that have the nice text that we can retrieve on. The text material are, there's a text tag. That's quite nice. So inside of text is all sorts of great text. But sometimes these documents are actually captions to go along with a photo. And the text tag might be empty. And you'll see instead a tag on those documents, graphic. And so we want to grab text out of those for our purposes, and as well the headline tag. Okay. The headline tag becomes metadata that you're going to store. It's like the title of the document that you might have. If it was a web document, it would have a title. For a newspaper article, it has a headline. And so we're going to store this in our metadata. These items, we're not in homework 1 going to purposely be dealing with them. You just need to know this for later on when we work in the term, that this is where the textual material is. But the headline, absolutely, we have that in homework 1 as metadata that we extract from a document and send to our metadata engine. Now our metadata engine is nothing special, and I'll say it now and I'll say it again later. I don't want anyone to install any databases. Again, we would like to be able to run your code if we need to. We don't want to have to install anything in addition to just getting the code up and running. So when it comes time to store the metadata, basically what you're doing is building, there's all sorts of ways that you could do it, but you're basically, again, dealing with some sort of dictionary where you're going to map from a document ID to a set of information such as the headline, the docno. And so again, the document ID is going to be your internal ID. So integers like 1, 2, 3, 4. And the metadata are things like the docno and the headline. And the homework tells you what else the metadata is. All right. I want to point out here now, before you run into it later in the course, you're not going to worry about it now, but I need you to be aware of this while we're talking about the topic of looking at the file format. So these are important things to know about the file. Ignore the document length tag, please. Okay. This is not what we will later call document length. We will be computing document length for our retrieval algorithm. It is not the value in this tag. This tag, this document length tag, is again part of the Los Angeles Times and their notion of how long the document is, that they wanted to tell people, oh, it's 600 words long. That's not our measure of document length. We're going to compute our own. So don't ever think you go grab the document length from the document length tag. You do not. Okay. So again, I've been talking about this, that we will internally refer to docs with an integer ID store integer IDs, okay? The first document you process, make it document 1 or make it document to 0, okay? Depending on whether you count from 0 or 1. Then the next document process, increment that, and so on. Now, again, when communicating with the outside world, that's us and our tools and our need to run experiments, we use the docno, this official identifier. Thus, we maintain two mappings. And this basically goes into the metadata portion that you're storing. We need a mapping that goes from the internal ID to the docno. And this is our standard lookup in the metadata portion. Yeah, I got a document ID here, and I need to get the docno. I need to get the headline for it. Okay, so that's the purpose of the metadata engine. It has to be able to take one of these internal IDs and give you other properties about the document. So one of them being the docno, this external string identifier. But as well, you also need to store a mapping that goes from the docno to the internal ID. Now, you don't need to store from the headline to the internal ID. We're never going to supply a headline to our system and say, what document has this headline? That's not a query that we're going to do, but we will need to go and say, I want to go see docno, whatever it is. And the reason is as a search engine designer, when you run results and stuff, or if you want to examine things that your assessors have judged as relevant or not relevant, you often want to be able to, like, I want to go see that document. I want to see what's going on. But what you have and you're keeping track of is the external docno. To ask the system to go fetch for you this one document and spit it back out for you, which you have to do in homework 1, you're going to need this reverse mapping. So you need two-way direction mapping for the docno. For all the other metadata, you just go from the internal ID to whatever the metadata is. All right. Now, one of the things is again, remember the snippet engine. It's in the snippet engine that we're going to store all these separate documents. For you, it's just going to be somewhere on your hard drive as specified in the homework. But you can think of it as your snippet engine. Stores the separate documents for fast retrieval. And you can store by internal ID or docno. If you store by docno, you will have to then look up, you will have to take the internal ID to docno lookup with the metadata to find that, but that's not a problem. You are not running things in parallel the way that a search engine is, so you're not going to go to the snippet engine and the metadata engine at the same time. You can go to the metadata engine first. It will send back, you get an internal document identifier, and you get back from it, yeah, I'd like to know it's docno, a headline, great. The date of it, wonderful, thank you. It gives you back that information, and then you could use that docno to your snippet engine actually and say, go fetch this, and I'll give you a scheme to do that. And the reason I actually like doing it by docno on the hard drive is, again, even though we're going to have you write a tool to fetch it, you could still find it and understand where that document is through its file name if we store it by docno. And again, we're just going to store these. I'll tell you, we're going to store these as a bunch of whole separate files. It's going to be our cheap way of building a sort of a database quick lookup. All right. Wonderful. Yeah, so I'll come back. Well, I just talked about it. Why don't I just go ahead and tell you this? So it's going to be stored in the Snippet engine. So when it comes time to store the document, what do? One of the things we're going to do is we're going to have, as I said, one document per file. This is an easy way of doing that. Just let's use our file system sort of like our own little database engine. We are not dealing with billions of documents here. If we were, this would not be the right way to do it. We're dealing with, again, about over 100,000. Easy for your file system to manage that for you. Let's just keep it simple and not involve fancier setups. Now, the one thing that you'll run into if you ever use your file system to the extreme is that you don't want to have more than about 1,000 documents per directory. What happens if you do start to put large amounts of documents in a directory, when you go and you use the user interface to be like, open up that folder, open up that directory, things grind to a halt. They're designed and they scale well to about 1,000 documents per directory. Don't exceed this. Otherwise, you'll pay the penalty as I have in the past. Let my mistakes guide you. Again, I think the nice thing is to name the files docno, where you don't actually name it docno, you replace it with the document identifier .txt. Make it txt again because you can open it easily and view it in a text viewer. Now, I did say that it's legal XML. So you wanted to, you could have it as .xml. And then it will open up most likely in your web browser and you'll see it nicely highlighting for XML. And it might actually lay it out really nicely for you that way. But they are easily readable as plain text files as well. Your choice. So if you want to do this, it just so happens that we know for every single document, it's embedded in the docno what the year, month, and day that the LA Times published that article on. And so you're able to extract, so each one of these, each has in it the year, the month, and the day. It's embedded into this. And so it's easy to extract out this part of the string. The format's always the same. And so you're always able to get the year. This is prior to the year 2000. Month and day. And so you can create a directory structure quite nicely, which is basically once you want to store a document, you extract from its name the year, month, and day. And if this directory doesn't yet exist on your file system, you can make it and so forth. And you end up with a directory structure, which is year/month/ day, and inside of this is where you put all the files. So you'll have, based upon the size of our collection, you'll have fewer than 1,000 files per day, which is great because I think it's a year's worth of the LA Times, and I'm telling you that there are about over 100,000. So the nice thing is we know that there are more than 100 days in a year, so we know that we'll end up with fewer than 1,000 files in each one of these directories. And so then we're able to nicely descend down and find this. As long as we know what the docno is, we can compute where it is on our file system and very quickly open it and read it in. And that's a really nice little, cheap little like database system for looking and fetching our docnos that we've stored. You will thus, I actually recommend that if you actually go to the trouble, I think it would be a good idea for you to have them compressed, but you might not want to bother with that. It's really not that much data. And if you want to view them separately by clicking on them, you just leave them uncompressed. Thus, you will actually have an uncompressed version of all the data on your file system. All right, great. Now we've done that. Let's look a little bit more at the actual format of these files and give you a better sense of them. So again, I said we're going to see them. They're going to come in here, and we're going to have a doc tag. So this is the file will actually start with one of these, and then you're going to see in the files that there is the doc node tag. And you're going to have the document identifier, and then you're going to have a closing doc node tag. Now, one of the things is that this identifier here has some leading and trailing white space. This is actually sort of a no-no for good XML usage. Again, keep in mind that these are very old files and people might not have been on top of everything. It's easy to read this way for the human, but the actual doc node does not include the spaces. So when you read these, be sure that you trim any leading and trailing white space. All right. And then there'll be other tags you'll see in them. And eventually, as I said, you're going to see a text tag in here. In most cases, most documents have a text tag in them. And then you're eventually going to find that there's a line that has the ending doc tag on it. And the reason I said you don't actually need fancy XML reader to read the file is that the doc and the doc end tag, so the start tag and the end tag for each document, do sit by themselves on a line. But it's easy enough to fetch a line and then just search the string and see, do I contain a start document tag? Do I contain an end document tag? And that will identify the lines that start and end. And yes, in this file, these tags are on lines by themselves, which makes it really easy. So it's not like you have to grab material after the start of the doc. No, the doc tag, it always starts after it as you come on down here. All right, and then it continues on, and you get another document that starts right up, stuff in there, and eventually there's an end to it. And then this continues and repeats. So there's just all these documents, one after the other in the file. Some things to note is that for those who aren't familiar with XML or markup languages like that, I want to say that you never see tags incorrectly nested. This is correctly formatted, so it's not. There's not really. You have to be super robust in understanding it. So everything actually does always have a legal setup with it, and in XML, these type of markups, tags are always properly nested. So if we start an A tag and we start another tag inside of it, we will end that tag before we end the A tag, before we end the enclosing tag. So everything in XML is always nested in this fashion. So if there was a tag that started inside of here, it would end inside of here before we got to the closing B tag. Illegal format is when people do things like they have an A, and then they go and they'll start their B, then they'll close the A, and then they will close the B. That's illegal. You're never going to have it like that, so you don't have to worry about those sort of setups. The way to really think about this is these tags behave like parentheses, or the way we would use parentheses, so that you know, we always would if we had square brackets and then parentheses and square brackets, this is the way that we correctly nest them, so they close inside of them. We don't ever believe that we would set it up with something along these lines, you know. We don't have an incorrect setup as follows. So the nice thing is, you know, that once you read an opening tag, if you wanted to grab everything in between them, you can just read until you hit the end tag and take whatever is in the middle of that and process it. All right. Now let's get to the overall simple algorithm for processing this file. And I do give a lot of guidance here on this first assignment. I want to be sure that you can be successful with it. I've seen part of the problem is this style of processing of opening up a file, streaming it off of disk, uncompressing it on the fly, and processing one document at a time where we're going line by line, and we never keep more in memory than one document's worth of material, is something a lot of students have never done before. And the idea doesn't even occur to them. They really do try to read everything into RAM because they're so used to like seeing stuff in Python and other languages which are like, suck the whole file in, then I will deal with it. We don't do that here. It's too big of a file to do that with. Or if you do it that way, you're sorry usually that you've done it. So let's not do that. All right, how to process the file. All right, this is the overall scheme. You've heard a lot of this already, but we're going to read the file line by line. And then we're going to be detecting the start and end of the document based upon the document tag, okay? So how does this go? There's a little bit more that people need to hear. So when you're reading it line by line, simply, if the line contains the start document tag, then you're at the start. And you're going to continue reading lines and appending them to a string buffer. So if you're going to read it in as one long string for the document, that maybe you're going to pass off to that XML processor, you'd use a string buffer. If you're in Java, you could just use a string in any other language, whatever works to efficiently do this. Or if you don't want to use it as a string buffer, or you just save the lines one after the other in an array. You just keep pushing and appending them to the array. Now, when you reach a line that contains the closing doc tag /doc, you are at the end of the document. And the whole doc is now in your string buffer. Or it's in your array. Okay. And this is available then for processing. And now you can say, ooh, I have one document, and you could send it off to, you know, a function to process this document, do the next things. And so you can envision you got this simple little loop, which is, ooh, I'm at the start of a document. Read lines and save them until I hit the end doc tag. Oh, I have all these lines, that's one document. Send it off to the process a document function. It processes it, does what's necessary, and then returns, and then the loop continues and fetches more lines, starting, finding the start of the document until it hits the end of the document again. It repeats until you're through the whole file. And this is how you will not end up saving more than one document's worth in memory at a time. You do not need to even save, for example, the mapping truly from ID to docno in RAM. You could certainly be writing that out to file per document. To do the revert, and likewise, you could even be having it set up so that if you wanted to, you could write out that mapping twice, once from the ID to the docno, the other time from the docno to the ID, but that's not actually necessary. So you can save in a file from internal ID to docno. And so that's like, oh, it's document 0. Here's the first docno. Document 1. Here's the next docno. And you could just keep writing those out to a file. So you'd leave that file open as the program runs, and you just write out those two things line by line. And then when the whole thing's done, you're going to close that file. Now, you're like, well, but I need a mapping that goes both directions. Yes. When it comes time that you need to run the search engine, you run that program, and as part of its initialization, it reads and opens that file. It reads the whole thing into memory, and in RAM, it then builds a dictionary that goes one way and the other way. So you have two dictionaries in memory, but you only need to store the data once on disk. Because on disk, it's just storing the data. You're not actually using it on disk as the data structure. You'll read it in, store it into two hashes, two dictionaries, whatever, one going from ID to docno and one from docno to ID. My apologies if I keep repeating myself. All right, next step to processing the file, step 2, is you send this full document, as I said, to your snippet engine, which truly is actually just a function that right now for you to do the processing that you need to do on it. What is it to send it to the snippet engine? Again, the snippet engine's job at this stage is to save that one document in a file on the hard drive in a way that you can later, given a docno or given a document ID, whichever one you want, you can go quickly know where it is on the hard drive, open it up, and return it and use it, okay? So that's all that function does, and we already talked about the storage of that. Then you need to send that document off and extract the metadata. Okay. Just a moment, please. All right. You need to extract the metadata. And so this is going to be things along the lines of the headline, the docno, the date, see homework 1. Okay, I specify it there. And you could send the whole document, or you could extract and send this to the metadata. So you could send the whole document to the metadata engine, or you could just extract the metadata and send to the engine. And that's really the proper thing is to, extract this stuff, now call something and say, here, metadata engine, save this, and send to the metadata engine. Now, you do not have a separate engine, of course. You're just writing one program. What this really means is you're going to need it in a data structure such that then it can be saved to disk. Now, you don't need to keep it in a data structure as you're processing stuff. Again, it can be as simple as, writing out a file where it's like you got a document identifier 1. And then you're going to have, you could do, if you want to, you can even do it separate lines. And next you could put the headline, then you could put your docno, and then you could put your date, and then you would be document 2, and you would repeat this. Later, when it comes time to actually run and use your search engine, again, in its initialization phase, it reads this file in and builds in memory a nice data structure, a nice hash table that maps from this to a struct that has these items in it. And again, you could do these per line, or you can always write them out one, and then you can have a headline, and you could have your docno and your date, and you could separate them with tabs if you wanted. Be careful though, because the headline, you know, might have some special characters in it. I hope it doesn't, but if it did, it could screw this sort of format up on you. Alternatively, you could, if you wanted to, you could go ahead. Another way to do it is to actually keep a hash table in memory. And so, all right, it's doc1. Here, this is the metadata. Store a mapping from 1 to this struct in the hash table for this information. And yes, and just keep it in memory. So the memory will grow as this program runs, but it's not going to be too much. All right. And then when the program is done, before it exits, you need to save that hash table to the hard drive. Now, again, you could write it out in your own format, or alternatively, if you're using something like Python, you could pickle the data structure, and pickling it then is a way to serialize it and write it out to a hard drive, and then those same tools will allow you to read in that object, and it'll all just read it in. So sometimes students really like to do that. They like to fill up whatever the data structure they have, for example, in Python, while the program's running, then use pickle it out, and then be able to read it back in. I don't know how to do that. I haven't done it, but some students like to do it that way. But you can also craft your own solutions very simply as well. But you're absolutely welcome to pickle and unpickle or whatever it is as you wish. And it's fine to hold it in RAM while the program runs, because eventually we're going to run the search engine and we're going to hold that in memory as well. We're not going to use a disk-based data structure for the metadata engine. All the metadata is going to come into memory. The only thing that we're going to keep on the hard drive in our search engine are going to be all the documents. So when it comes time to make the snippets, yes, then we'll fetch like the 10 documents that we want to show to the user and build snippets. We won't even keep the inverted index postings on the hard drive. We'll actually read the entire inverted index into RAM. So we'll have the whole inverted index in RAM, and we'll have the metadata in RAM. We'll have the lexicon in RAM. And so it'll all be a memory-based search engine, except for when the snippet engine needs to run. So you don't have to worry about having good disk-based data structures for the metadata engine, for the lexicon, or the inverted index. We'll keep those all eventually in RAM. All right, so after we've done that, that's basically it for homework 1. Okay, we will continue on in our later homework. You will extend this work to extract text. This is basically, you don't want the tags. So there'll be things like paragraph tags and other stuff, other junk inside of the text tags. And so we'll want to extract the text without those tags. And then send this to the tokenizer, which we'll eventually talk about very soon, actually, and then send to our lexicon and get back term IDs or the term numbers, and we'll work to build the index. But we're not going to be building our index in homework 1. We're mainly just processing the documents, building out our metadata and our snippet engine storage. All right, and then 5, repeat till done. You know, so yes, one file at a time. Keep repeating this thing over and over and over again. All right, so that's the guidance that I have for homework 1. I hope that helps. If you need any additional help, of course, Campus Wire, and I'll be able to answer the questions. Again, homework will be out as soon as it can be out, but it will take a while. All right, thank you.